Oi, mixture of a million experts. What is good, YouTube? I'm a bit late to this paper by a few weeks. I hope you appreciate my breakdown of it, probably more technical than most, I would say. This one's cool. As you'd expect, it's an extension of MOE, just taking that even further. Pretty clever tricks in here. The issue, of course, being that for it to be feasible actually long term, it would probably need some specific hardware implementation. But given that it's a DeepMind paper, and given that the hardware implementation isn't that crazy, I wouldn't be surprised if NVIDIA jumps on board at some point just to be encouraging. Before we get started, like, subscribe, comment, all the YouTube things, join the Discord to discuss, link in description, support me on Patreon or with that YouTube join button down below, as low as $1 per month if you're a frequent viewer. And if you do that, you will get early access to my videos before they actually go up. And with that, let's get to it. So we know, given all of the things equal and using compute optimal everything, MOEs consistently outperform dense models in terms of flop efficiency, right? But even past that, they introduce granularity, aka the number of active experts, as a new scaling axis, and empirically showed that using more of these experts does improve performance. The clever thing this paper does is extrapolate that scaling law and suggesting that continued improvement of model capacity would ultimately lead to a large model with very high granularity, very large number of experts. And those experts, I guess by definition, would be very tiny in order to fit, right? Even beyond the scaling laws, though, the other reason to have way more experts is for sake of lifelong learning, where so far MOE has done pretty well. The best example being cases where you can just add a new expert, and as long as you can figure the regularization thing out, they can actually, MOE models can adapt to new data streams. It's kind of a hacky way to get there, but freezing old experts and updating only the new ones does prevent catastrophic forgetting and maintain plasticity, or I guess I would say create a temporary regime of plasticity until the new experts get fully saturated. So in this paper, the author introduces a method called peer parameter efficient expert retrieval that leverages key retrieval to efficiently route to an extremely large number of experts, kind of decoupling the parameter count from actual computational cost. Let's hit the math then, right? So a peer layer is just a function from an n-dimensional vector to an m-dimensional vector that consists of three parts. First, we have n experts, where capital N, sorry, where I suppose the lowercase n earlier, where each expert is itself the same type of function or same shape, I should say, from an n-dimensional vector to an m-dimensional vector, and each one of them correspond to a product key, which itself is a d-dimensional vector, right? And then we've got a query network, which is a function from an n-dimensional vector, aka same input as you mentioned first, onto a d-dimensional vector, so same as the product keys, which maps the input vector to a query vector. So nothing too new here. We're just retrieving the top k experts according to said keys, computing router scores, and aggregating expert outputs. This isn't too crazy. Right here, we'll get into how the actual product key retrieval and everything works. But fundamentally, think of these experts as just, instead of being their own full feed forward networks, they're very tiny experts, meaning you're grabbing just a single vector dot product each time. So you were kind of composing a unique feed forward layer with a bunch of different rows of experts according to whatever top K worked, where every single row of every matrix in the feed forward layer is itself one of these little experts. Now, if we're using an actual million experts, that's obviously computationally not really feasible to do it just naively with the top K indices. That'd be way too expensive. So instead of using n independent d-dimensional vectors as our keys, we create them by concatenating vectors from two independent sets of d over two dimensional subkeys, right? So now we have two sets of vectors that are half the size of what a key would otherwise have to be. All we have to do is concatenate those two half-size vectors together to get a full key. And what this allows us to do is it means that our two sets have cardinality square root of n. So in practice, we of course choose n to be a perfect square and d to be an even number so that they're both easily to split up. But now suddenly we only have two square root of n functional actual separate vectors to use as keys, each of which is half the size of the original keys, and we're going to then be concatenating them in every possible combination to get our full set of keys. So instead of comparing our query vector to all n full-size original keys and selecting the top k of those, we can instead split our query vector into two subqueries, q1 and q2, and apply the top k operations to the inner products between the subqueries and the subkeys respectively, right? So in a normal setup, you have a query vector of length d, and you have a key vector or a bunch of key vectors of length d, and you have to now do n total inner products and then top k it, right? Whereas now what we're doing is, because we have these splits both with keys and queries, now we are taking two query vectors, each half the size, inner producting them with our far fewer number of half the size key vectors and getting out two separate sets of top k indices. And so now from our top k operator, we end up with a total of k squared candidate keys when you look at all combinations. And in this k squared set, it's mathematically guaranteed that the k most similar keys and full-sized, if we were to do the full-size product, do actually exist in this candidate set of k squared half-size keys. So all we have to do is apply the top k operator again to these k squared half-size inner product keys, and then for those k largest ones, add them together, or sorry, add together the concatenations, right? And this will give us the mathematically equivalent same top k matching keys from if we had done the original full-size set, effectively reducing the complexity of our search through a million experts by a lot, from what is this, OND to O square root of n plus k squared d, blah, 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 blah. But it's a much more computationally efficient way to do this, that this really wouldn't be very feasible with a million experts if we hadn't done this clever key splitting mechanism, right? So as I said earlier, we don't have an actual entire feed forward layer MLP with the whole deep hidden layer. Instead, every expert is a singleton MLP, meaning it has only one hidden layer with a single neuron, so it's just vector dot products as opposed to actual full matmuls. And interesting here, they do a kind of multi-head setup, similar to multi-head attention, where they use H independent query networks. So that whole query thing I described earlier, they do it in parallel H times, right? Each computes its own query and retrieves a separate set of K experts. However, different heads share the same pool of experts with the same set of product keys. So it's really like, what's it called, multi-query attention, where you have a bunch of different queries but the same keys to be shared. And in this case, the expert is analogous to the value that gets shared in MQA, right? And then really simple, given the nature of we are kind of constructing an entire feed forward network out of these individual singleton feed forward networks, all we have to do at the end is sum it all up. And so the way to look at this is that H, the number of heads, is equivalent to the number of hidden neurons in a regular feed forward MLP, right? So if you were to only retrieve one expert, so k equals 1 in our earlier top k setup per head, then this would all just reduce to a regular feed forward network with H hidden neurons. Meaning, again, Peer kind of dynamically assembles a new feed forward network with H hidden neurons. And here, the number of experts, if you actually look at it in terms of, oh, well, how many feed forward networks are we doing, is just equal to K, as you would expect in a regular MOE setup. Now, here is the big asterisk with this paper, is that an efficient implementation may require specialized hardware kernels to accelerate embedding lookup and fusion. This is the difficult thing, is it's not straight matmuls, is it is now we are doing lookups to dynamically construct these effectively regular feed forward experts. But at least as of now, and I'm not a hardware person, I can't speak on this, regular matmul, a regular feed forward layer would be much more efficient, and that this lookup time, looking up across different rows in an embedding table, takes relatively longer. So for our actual results comparison, we're going to look against a dense model, an MOE, some other paper called a PKM that I didn't bother to actually look through, and of course our own new peer method here. And instead of doing every single layer in the model. We're just doing within a 12 block transformer, presumably this is GPT-2, I don't know. We're only replacing the feed forward network in block 6. So it's going to be a regular dense model, except one single layer in the middle at the index 6 will be replaced by either MOE, whatever PKM is, and our new peer method. Specifically in peer, we're using 10 to the 24 experts, which should be around a million or so, with H heads and a top K of 16 experts per head. And then apparently batch norm is necessary to increase expert usage. I guess it's the equivalent of our regularization in regular MOE. And here are the primary results you wanted to see, of course. I've got peer highlighted. It is the lightest blue color. And as you can tell, as you would expect, the isoflop comparison, we do end up with peer as it is a natural extension of the scaling laws we already knew of with MOE models. It is just better being down further to the right. So on the x-axis, we have parameters, and then on the y-axis, we have perplexity. And for a given level of parameter count, we do end up with lower perplexity as compared to the base model. Now, of course, a dense model, by definition, has fewer parameters, but this is also comparing, remember, total parameters versus active parameters, right? So in a dense model, all the parameters are active during inference time, whereas the MOE as well as the peer, you have most of the parameters of that MOE peer layer are not actually active. And so even though it seems like we're having way more parameter count, of course, in reality, our active parameters are equivalent, just with the added hiccup of we now have to do those computations, those calculations to actually pick said experts, which isn't a huge deal in a very tiny router with a traditional MOE setup, is a bit bigger of a deal to the extent where we might even need new hardware if we actually wanted to use peer. But if we can get new hardware that works with it, it does very clearly show much better results, at least in this initial isoflop comparison. Here we have perplexities on some general language modeling data sets, the pile, C4, etc. And as you'd expect from the loss curves, we do in fact have peer beating out everything else, the MOE, the PKM, and the original dense model. Now on this graph to the left, we vary the total number of experts while keeping the same number of active experts, right? And as we can see, this blue line, smooth decline right here, as you go from fewer to more total experts, we do get better results. And then this graph on the right, we vary the number of active experts. Keep in mind this requires messing with both the H, number of heads, and K, the top K parameters in order to make this actually work. But so we have H times K is number of active heads, right? Or number of active experts, my bad. And we do this on the right, on the graph on the right, while keeping total number of experts the same. And we do in fact see that as this goes down, right, more experts active is in fact useful, but it seems like there is a cap out at a certain point where we get some pretty stark diminishing marginal returns. There's a really big gap between 32 and 64, and then from 64 to 128. But the gap from 128 to 56 and then from 256 to 512 is relatively small and decreasing. So we probably don't want to just keep going forever in terms of active number of experts, in terms of what is compute optimal. So while active experts increasing is certainly useful, its usefulness is diminishing as you go up. And of course, the device memory consumption is the big deal that will limit us in that regard, as it does with a number of top K experts in regular MOE. Now, here's a big question. Given that we have a million experts, you might be wondering how many of them actually end up selected during inference and whether their usage is evenly distributed. Because you know in MOE, it's a huge issue of regularization if we end up with dead experts or just rarely used experts if you're even lucky. And getting actually evenly used experts is tough. There's even the question of like, do we want perfectly evenly used experts given that some tasks might just be more common than others? It's a tough question, and you would expect, or you would assume, I would imagine anyways, that if we have a million experts, I would not be surprised to see some crazy number of 70% don't even get used at all, right? So let's see. But surprisingly, even for a million experts, the usage does end up being close to 100%. And the reason we mentioned batch norm earlier, batch norm specifically doesn't prevent dead experts, but it leads to more balanced utilization of the experts that are used. And generally, thanks to that, lower perplexities. So you see a without batch norm as the darker line and with batch norm as the lighter line. Not a huge difference, but certainly worth doing batch norm right here, right? That is it for today. Hope y'all enjoyed. Like, subscribe, comment, all the YouTube things. If you're a frequent viewer, join the Discord to discuss. If you really, really like me, consider supporting with that YouTube join button down below, as low as $1 per month. And you now get early access to my videos when they actually get recorded versus when they go up. They go up maybe even weeks later, kind of thing, right? So go check that out. Thank y'all for watching. End of video.